the unusual that happens.
Hey,
Hey Ash, what's up?
um, I have to go drop off my mom. Um,
Okay.
join the meeting a little late, if that's okay.
Yeah, that's fine.
Okay, thanks.
You're welcome. Well, good morning, guys. I hope you're doing well. We are at the end of another week and have got through some more material. There is only one more topic after today for this term. So we will be doing a lecture today. I will be covering the exam. I think I'd rather do that on Monday because I haven't released the grades yet. They're done, but I haven't released them yet. I'd like you to have a chance to look at those before we go over the test. So I think I'd like to do that first thing on Monday. We will still have time to finish the lecture then. And of course, we have Wednesday available if that's required as well. We can also do a bunch of prep next week for exam 3 and the final. So depending on how that looks. I don't think that that's going to be an issue. The lab final is also next week, and there's material on D2L for both of those. If you actually, let me show you that. In the D2L shell, you'll see under the practice for the final exam, not only their sheets for the final itself, but also for the lab exam. So all of this stuff is related to the lab exam. So that is stuff related to both of those. So the lab exam is slightly different than what you'll see in the final exam itself. That is mostly related to the calculations and things that were done with the laboratory. So hopefully you will be okay with that. But if you have any questions, comments, problems, I'm more than happy to talk that over with you. So do we have any questions before we start today's material? Okay then. So what are we going to be talking about today? Well, today we're going to be talking about the properties of liquids, types of solutions that we have. We'll go over the concentration units again. Remember, we talked about them previously in the aqueous solution section, but we're going to talk about them again because we're going to need most of them to do what we're doing today. We'll talk about the effect of temperature on solubility for both solids and gases. We'll talk about the effect of pressure on the solubility of gases. And then we'll talk about colligative properties. And we're going to do this in two separate sections, one for non-electrolytes and one for electrolytes. It's a minor change between the two, but that's the way we're going to handle it. Colligative properties are things that are based on the amount of material, regardless of what that material is. And they include things like vapor pressure lowering, fractional distillation, osmotic pressure, boiling point elevation, freezing point depression. And then, of course, we can use colligative properties to determine molar mass. So that is another thing we can do with that in the laboratory. We'll talk about how the electrolyte solutions change that. There is a laboratory that goes with this. You'll be doing a freezing point depression, and actually it goes much better in the virtual lab than it ever goes in the physical lab. You'll actually be able to see that. So hopefully that will help you to understand what that topic is about. Okay. But of course, before we get into that, let's do a little bit of review from what we talked about the last time. So last time we were talking about intermolecular interactions. All right. We also talked about phase changes. So when we talk about phase changes, if I'm going to go from solid to liquid, that's melting. Gas to solid is deposition. Gas to liquid is condensation. Liquid to solid is freezing. Solid to gas is sublimation. And of course, liquid to gas is vaporization. Okay, so all of those are the terms that we would use for those. Now, that's not all of them. That there are a couple that are missing from that, but that's what we're looking at there. So you may get asked for this transition, what is the word that's associated with that? One of the other things that we talked about, tell me what compound this phase diagram is for, and how do you know? So I said that you'd get a question like this, and you of course will, because I love to ask them. This diagram right here, based on what I see, and what I'm looking at is this line right here. I can see that that is a negative slope. Because it is a negative slope, this is water. It is not anything else. It is just water. Okay, and that is the answer that I'm looking for there. If the slope was the other direction, if it was positive, then it could be anything. The answer that I'd be looking for there is not water. And of course, that's because of the slope of that line. Okay. So are there any questions about that part of it? Okay. So let's talk about some of the properties of the liquids. And of course, this is all based on those intermolecular interactions. Okay. Remember that we talked about a number of different types of intermolecular interactions. So we have our van der Waals, which you may also see as Linden, or dispersion forces. All of those terms are used, and they really all refer to the same kinds of things. So we kind of combine them together and don't talk about them separately anymore. So there's that one. That is the least, the weakest of them. We then have our dipole-dipole interactions. If our two molecules have dipoles on them, we then have a dipole ion interaction, or ion dipole if you prefer it that way, which is also between molecules that have a dipole and then with an ion with them. Oh, sorry. And our last one that we talk about is hydrogen bonding. And again, hydrogen bonding is an OH, FH, or NH bond. Okay, so those are the only atoms that are capable of having hydrogen bonds, are those. So all of those interactions lead to differences in these materials. So if we only have those van der Waals interactions holding things together, then there's not as much energy that's required to move that material. If we also have dipole-dipole interactions, then more energy is involved. If we have ion dipole interactions, more energy is involved. And hydrogen bonding, even more energy is involved. It's a much bigger difference for that hydrogen bond. When we talk about surface tension, we're thinking about the top part of a beaker, right? So just a beaker, cup, whatever. We're looking at the top part of that solution. So that solution inside of itself is pulling everywhere. All those molecules are pulling on each other. But at the surface, the only ways that they can pull are down and to the sides. Okay, that means that we end up with tension that exists at the top of that liquid. Okay, and the tension is a measure of how strong those interactions are. So the stronger those interactions are, the more energy we're going to need to break that tension. Okay. So it's a measure of the energy required to stretch or increase the surface area of a liquid by a unit area. One of the things that we see due to surface tension is what we call capillary action. So if you've ever taken a piece of glass and put it down into some water and watched as the water comes up into that tube, that is capillary action. What happens is that those molecules cohere to each other, so they are in contact with each other and they stick together, but they also have adhesion to the walls. So water especially can interact with those walls, and that interaction between the two of them pulls it up. And that's why we end up with the meniscus looking the way that it does. Because what actually happens is that the water goes up further along the walls than it does in the middle. And that's the formation in the meniscus that we see, okay? So that's because of the interaction at the walls, right? Water has a higher than expected surface tension, and that's due to its dipole-dipole interactions, and specifically due to the hydrogen bonding. Because each water molecule has the capability of making two hydrogen bonds, that gives a lot more energy that we have to be able to use to get that thing apart, okay? One of the other things that we talk about in terms of our solutions is the viscosity, okay? So that's a measure of a fluid's resistance to flow. Typically, when we talk about viscosity, the way that most people encounter this is we talk about materials that don't flow very well, like molasses. It is very difficult to get molasses to flow, and that's because it's a highly viscous material, okay? So it's usually a lower value as temperature increases. So generally speaking, as we increase the temperature, the viscosity goes down, okay? Strong intermolecular forces mean higher viscosity, okay? Now, water, due to the hydrogen bonding, is higher than similar liquids, okay? Things that are roughly the same size but don't have that hydrogen bonding, okay? Like an H2S doesn't have that hydrogen bonding. That energy is a lot different than it is for H2O, okay? And of course, that brings us to water. Yay, water's weird. And that's actually really fun and really important scientifically. And it has a lot of strange properties because of that. Now remember, when we talk about our water, we have two lone pairs, and then this hydrogen, and this hydrogen, and we have a net pull of electrons this direction, which means that this has a permanent dipole. Okay, it is a polar molecule, and that's because of those lone pairs. Okay, so we have more electron density on one side of this. This then means, and of course, this lone pair can interact with another water to do some hydrogen bonding there. We can also get that same kind of thing down here. So we end up with the ability to do that in two different places, and that leads to some very interesting properties. It leads to high surface tension, high viscosity. It gives a high specific heat, which is how much energy we have to put into this to get it to change temperature. And the density of water is higher than ice, okay? So the water has a higher density. That's because when we make ice, we have this formation of those hydrogen bonds that gives us more space in between them. And that's an unusual property, okay? It's not normal for us to see that. So questions about that? Now, of course, we have to talk about our types of solutions. Now, any solution is something with something else in it. That's what we mean. We can have a gas-liquid solution. So if I have a liquid solution that has gas dissolved in it, an example, excellent example, soda has CO2 in it, right? So it's a liquid solution that contains CO2. Now, that soda also contains some particulate matter that has been dissolved, so we don't see it, okay? But that is in there as well, all right? Now, the solid-liquid interactions. We can have a liquid solution when we put a solid into it. Example, sodium chloride in water, okay? That's a fairly common one that we do. Often when people are cooking pasta, they'll put table salt in that water. And of course, there are lots of reasons that are given for why this is done. We'll talk about what the scientific reason is for doing this so that we can talk about that later, but we'll get to that. We also have liquid solutions that we have. When we have a liquid solution, we put a liquid into it. And we've talked about this before with our solute and our solvent. Okay, so ethanol and water is one of the things that we've talked about with that. So whichever one is present in the higher concentration, higher amount, that's going to be our solvent. What we put into it in the smaller amount is our solute. Okay, so those are the types of solutions that we have. All right, gas, liquid, solid, liquid, and liquid. We also have some terms that apply to those solutions. One is saturated. And what that means is that it contains the maximum amount of solute that will dissolve in a solvent at a specific temperature. So what we notice as we, for instance, add sugar to tea, right? We get to a point where it disappears, and then it stops. And suddenly you've got it sitting on the bottom, all right? That's when we've reached that saturation point, is the point right before we start seeing it on the bottom. That's our saturation point, okay? Now, if it's unsaturated, if I add more material to it, that will still go into solution. So it contains less than the maximum amount of solute that will dissolve in a solvent at a specific temperature, because it says temperature dependent. We also have a situation called supersaturated. And so one of the ways that we do this is if we take some sugar, we put that into water, we raise the temperature on that, and then we just let it cool. So we don't do anything to it. We leave it undisturbed and we let it cool. It turns out that that sugar is not going to fall out of that unless it's disturbed, okay? And that it doesn't take a lot to disturb it. But if we manage to get it to do it right, then it's fine. And then we can stick like a piece of wood in it. And when we do that, that gives it a nucleation site. So all of the sugar that shouldn't be in that solution, that's in there even though at that temperature it shouldn't be, will clump onto that nucleation site that we put in, that stick, okay? This is how we make rock candy, okay? That's a really interesting thing that we're able to do because we didn't disturb it, all right? So that's what a supersaturated solution means, is that we have more in it that should be there, all right? And that's because we've been careful about how we set that up. Okay. So those are our terms in terms related to saturation. So saturated, unsaturated, and supersaturated. Now, concentration units. We talked about this very briefly before. We have a percent by mass. Percent by mass is the mass of the solute over the mass of the solution times 100. So that's used for things where molar mass is unknown. It is independent of temperature. Okay, so if I don't know what that material is, I can calculate a percent by mass and report that as a concentration, because if I don't know what it is, then it's not possible for me to tell you what the molarity is. Okay, I can't tell you what the molality is, because if I don't know what it is, then I can't calculate the number of moles. We can also talk about a mole fraction. Okay, a mole fraction for component A is listed as chi A. This is called chi. So chi A is equal to the moles of A over the sum of all the moles. So total moles that are present. It is a fraction. We use that for partial pressures of gases, calculation of vapor pressure. It is necessary for us to know what fraction is due to what component, and I'll show you how that works in just a few minutes. Okay. We also have molarity, which we've talked about in pretty good detail now, which is the number of moles of solute per liter of solution. And that's the most typical way that we talk about concentration. So if you get a question that says, what's the concentration, and they don't specify, it is always asking about molarity, which is this big M, moles per liter. Okay. It's very easy to measure. It's very common for us to use it to discuss solutions for titration and gravimetric analysis. So if I'm doing an acid-base reaction, if I'm doing a precipitation reaction, and I'm using that information to calculate the concentration of another solution, that's one of the things that we use that for, okay? We also have a term called molality, because the thing that you may or may not note is that this is in liters of solution. Well, the liters that I have are dependent on the temperature. So as I raise the temperature, that volume changes. It gets bigger as temperature goes up. So this is temperature dependent. My molarity is dependent on T. Molality, on the other hand, because of the way it's defined in kilograms of solvent, this is temperature independent. And that's really important if we're talking about doing things where the temperature is going to be changing. So if we're talking about freezing point depression, boiling point elevation, we're looking at changing those temperatures. So we need a measure that is independent of the temperature. Okay, so that's when we use molality. Molality, small m, and of course it's supposed to be italicized, is the moles of the solute divided by the kilograms of solvent. Okay. Typically, if I want to convert between the two, I need a density to be able to do so. We'll talk about that in a few minutes. Like I said, this is independent of temperature. It's used for calculation of changes in boiling points and freezing points. It's typically why we use it. Okay. Now, are we going to need to be able to convert between these things? I'll give you some examples where I ask you to convert in between them. Yes. But that is not something you will see on a test. What you may see is that you're given a molarity and you need to find a molality to be able to do a calculation that you've been asked to do. Okay, so that's a fairly common thing. You may be given a molarity and then they want you to calculate a vapor pressure change, which requires you to go from molarity to mole fraction. All right. So it is necessary to be able to convert between them, but it's not something that we see typically as a, hey, convert these to new units kind of question. Okay. But that is how we're going to look at it for the moment. All right. Questions so far? So concentration calculations. We're going to do a couple of them here. Commercial vinegar is essentially a solution of acetic acid and water. That's what it is. A bottle of vinegar has 3.78 grams of acetic acid per 100 grams of solution. Assume that the density of the solution is 1 gram per milliliter, which it is because it's fairly low in terms of the solute. And acetic acid has a molecular weight of 60.05 grams per mole. Okay, now acetic acid is CH3COOH. Okay, so it is 60.05 grams per mole. All right. I want to calculate molality, percent by mass, and my mole fraction. Okay, I did this in that order because it's most common for us to calculate molarity, then molality, then percent by mass, then mole fraction. So in terms of how often they occur, that's the order of occurrence. So that's why I did it in that order. Now, if I want to calculate a molarity, my molarity is defined as moles per liter. All right. So since that's moles per liter, that means I have to start with my 3.78 grams of acetic acid. I need to divide by the molecular weight of the acetic acid, because if I do that, that cancels the grams and gives me an answer in moles of acetic acid. Okay, so that tells me how many moles I have. Now, if this is a 100-gram solution, okay, and it's 1 gram per milliliter, then I have 100 milliliters. So I can divide that by the volume in liters, 0.0629 moles in 0.1 liters, and that gives me 0.629 molar. Okay, so moles per liter. Okay. So again, I don't normally set this up as multiple calculations, but it's perfectly fine for you to do so. And again, one of the things that I talk about is weaned out, convert to moles. So I converted to moles, and then I looked at my definition and said, okay, I need to get that over the liters. So let me manipulate this to get those liters that I need. All right. So that's my molarity. Now, I'm going to look at my molality. If I want to do molality, that's moles per kilogram of solution. And this is solution as well. Okay. So if my molality is moles per kilogram, and I know that I have by that 0.0629 moles, because we calculated that previously, and that calculation will not change here. We have 100 grams or 0.1 kilogram in this particular solution that we're looking at. So I can take that 0.0629 moles divided by my 0.1 kilograms, and it gives me 0.629 molality, or little m. And everybody goes, well, they're exactly the same, then why do I care? Well, they're not always going to be exactly the same. So my density on water is only 1 gram per milliliter at a very specific temperature. Okay. Anytime that we're not at that temperature, that density will not be 1. And it isn't 1 if I'm not in water. Okay, so any other solution, that density is going to be different. So we need to make sure that we know how to calculate that so that we can deal with it. Okay. Now, if I want to look at a percent by mass, I need a mass of my solute over the mass of solution. Oops, that should be solute, not solution. I apologize. That one's solution. This should be solute. This one's solution. And that's a percentage, so we multiply by 100. Yay, awesome. Okay, percent by mass is the mass of the solute over the mass of the solution times 100. I have 3.78 grams of the acetic acid for 100 grams of that solution times 100. That's 3.78%. Okay, so there's that one. And the last thing that I want to be able to calculate is a mole fraction. And remember that my mole fraction is the moles of the solute divided by the total number of moles. And this is not a fraction, so it's not multiplied by 100. It's not a percentage, so it's not multiplied by 100. It is a fraction, so we want it to be less than 1. If it comes out over 1, then there's a problem, because it should be less than. So chi A is equal to the moles of A over the sum of all of the moles of all components. I have 100 grams of solution, but that 100 grams contains 3.78 grams of acetic acid. All right, that means that I have 96.2 grams of water that are present in that mass. Okay, that 96.2 grams divided by the molecular weight of the water, so that 18.02 grams per mole, gives me 5.34 moles of H2O that are present in this solution. Okay, so my moles of acetic acid is going to be equal to that 0.0629 moles that we calculated in the beginning, divided by the total, so the 0.0629 plus the 5.34 which is this 5.4029. And that gives me 0.00116. Okay, now that's the one for the acetic acid. I can also calculate a mole fraction for the water, in which case I look at the number of moles of the water divided by the total number of moles, and that gives me this 0.9884. The sum of those two should be approximately 1. It may not be exactly 1 because rounding, it happens, but that's what we should be looking at. So questions about what we did or why we did it. Again, for me, this is all about what are the units that I need. So moles per liter for molarity, moles per kilogram for molality, mass of the solute over the mass of the solution for percent by mass, and the mole fraction is going to be the moles of the solute of the total number of moles. Okay, when we consider that mole fraction, we need to remember that we have to take out the mass of my solute from the mass of the solution that we have. Okay, all right, awesome, possum. Questions, comments, problems on that? Okay. Now, when we talk about temperature and the effect on solubility, for most solids, the solubility increases with increasing temperature. As I raise the temperature on my tea, more of that sugar goes into it. As I raise the temperature on my water, more of the salt that I put into it goes into that solution. There is one notable exception for anybody who cooks. Cornstarch is a notable exception because cornstarch is only soluble at really low temperature. As I raise the temperature, it becomes thick, and that's a thickening agent. And that's because as it gets warmer, it's less soluble. Okay, so that's what we're looking at there. Now, understand that there is little to no correlation between the heat of solubility, the delta H of the solution, and the change in solubility with change in temperature. So even though these values here can be referenced in a table, they can, okay? That has very little to do with how much I'm going to be able to dissolve if I change that temperature. So I can't use that to predict how much I'm going to be able to get into the solution at a particular temperature, okay? One of the other things that we can talk about, fractional crystallization. What that means is the ability to crystallize one component of a solution versus another component, okay? Sometimes, and it doesn't always work, but sometimes, if we set our conditions correctly, we can separate two components that are in a particular solution in terms of getting them out of solution, and we do that through distillation. So it's fractional distillation where we get into the gas phase and then collect the pure material. We can also do it by making it a solid and then collecting that solid. But that requires that there is enough of a difference for us to be able to do so. All right. Fractional crystallization is possible since solubility changes very differently depending on temperature for different materials. So if I have the exact same solubility at one temperature, but only one of them is soluble at another temperature, then I can precipitate out one of those materials, but not both of them. It's a very common technique that is used for separating things. And if you take organic chemistry lab, you will do it ad nauseum. It happens all the time because that is one of the purification methods that's used after we synthesize something. Okay, so that's fractional crystallization. All right. The other thing that we need to talk about is the solubility of the gases. All right. Now, if I consider the gases, the solubility of the gas decreases with increasing temperature. I talked about this a little bit yesterday or on Wednesday because I said that as those gas molecules have more energy, they are more able to escape the surface tension, and therefore they are more able to be in the gas phase. All right. So that's easier for it to get out of that liquid phase, and therefore we have less gas in solution. Okay, this is part of the reason that sodas are stored cold, because it keeps all of that CO2 in solution so that it's still carbonated when you open it to drink it. Okay, notice that the carbonation goes down as the temperature goes up, okay, and as it's open to the atmosphere. All right, both of which lead to decreases in the solubility of that gas. All right. All right. Now, one of the other effects of this, Henry's law says that the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. Okay, so the amount of gas that will dissolve in a solvent depends on how frequently that gas molecule collides with that solution. Okay, so if I've got a situation where I have some gas above this particular solution and it's tied there, it can't get away, then the more of it that I have, the more I'm going to get into solution, because its ability to hit that liquid goes up. Okay, this is why sodas are given the space that they have between the top and the bottom, and we put in an overpressurization of carbon dioxide because that drives that carbon dioxide into that solution. Okay, so we get more of it in the solution, we keep more of it in the solution because the temperature is low. So all of those things work to keep that thing being carbonated when we open it. Okay, so higher atmospheric pressures lead to more gas molecules being dissolved in the solution, and that's exactly what we're talking about, making sure that pressure is really high above it to keep it in. Okay. That's not what I wanted to do. There you go. And now we move to colligative properties. Now, I love colligative properties. I think they're really interesting and they lead to a lot of really fun things that I never would have expected. So I think they're fun. Colligative properties are properties that depend on the number of solute particles in solution, but not what they are. It does not matter what they are. It could be anything. All right. Now, if they ionize, that's a slightly different thing. So remember that sucrose, C6H12O6, is not going to ionize. It doesn't come apart when it goes into solution. So it remains as one particle. But something like sodium chloride, which is ionic, comes apart and becomes two things in solution. Now we'll talk about that effect a little bit later. We're going to talk about how things work, what happens without considering that first. Okay. So if we look at our molality concentrations, again, molality is mol, that's moles of solute per kilogram of solvent, temperature independent. We're going to use that when we talk about those temperature changes. One of our colligative properties is called vapor pressure lowering. All right. What that means is that solutes do not have an appreciable vapor pressure on their own over a solution because there's not that much of them present. Okay, so very small amounts of them means that it's much, much harder for them to get out of solution. Statistically, it's less likely that they'll be out of solution. Okay, so they don't typically have that high pressure. But if we look at the solvent, right, its ability to get into the gas phase from the solution has been lowered. And the reason that it's been lowered is because those solute molecules may be at the surface, preventing those solvent molecules from getting out. Okay, so we lower that vapor pressure because of that. And that is entirely dependent on how many of those solutes I have in my solution. So we look at a mole fraction for that. So the pressure that we'll see in a solution is different than the pressure that we would have over a pure compound. And if we look at this being our pure compound, P01, that's standard state is what that 0 stands for. So if it was by itself, that's the pressure that it would have under those conditions. And when you multiply that by the mole fraction of that thing, that will tell me what the pressure of that material is. Okay, so if I add stuff to this, then I can figure out how that pressure is going to change. All right. The solution with solute is less ordered, so it is more favorable because there's less order in it, and that's important because less order is good. We tend towards less order. I mean, look at your room. If you don't put any energy into it, it tends to disorder, right? At least mine does. So I hope that happens for everybody. Now, it's that more favorability means it's less likely to vaporize because it's better for it to be in that solution. Okay, so we can calculate how much the vapor pressure is going to change if we know what it is before we put stuff in it, and we know what the fraction of the stuff that we put in is. Okay, questions about that? One of the other things couple of other things that we talk about, fractional distillation. So I mentioned this a couple of slides ago. This is the separation of liquid components based on their different boiling points. So if we have two materials with different boiling points, I can boil them and collect the vapor to condense it. So if I boil something in a distillation apparatus, there's coils of cool water above where I'm boiling this. So as it boils, it hits those cool coils, and then we can collect that. And it's set up in such a way that we can do that. It's obviously going to collect the thing that is most in the vapor phase. So the thing that has the lower boiling point will be the thing that's most in the vapor phase. The vapor is higher in concentration of the material with a higher vapor pressure. Again, lower boiling point, higher vapor pressure. And we can repeat this process. So each time that I do this, I end up with more pure material, right? So I do it once and okay, I got more pure material. But if I do it again, it's a magnified effect because now I'm starting with something that was much more pure. Okay. This is called repeated distillation. This is commonly used. In my head, I always see MASH when I think about this because they had a still that was set up for them to make alcohol. So they were able to distill the alcohol that they had used to purify the part that they wanted and get rid of all of the other crap. This is actually done for most alcohols before they're sold to you, they're distilled. So that happens for most things. And I think it's a really interesting process. Okay. Now, other things. Osmotic pressure. Yay, osmotic pressure. So osmosis is the selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. Okay, that's my dictionary definition of osmosis. When we talk about osmosis, we have a membrane. This is called a semi-permeable membrane. And what that means is that the water can move through it, but whatever is in solution cannot. Okay, so if I have different concentrations on the two sides of this, so this is a 1 molar solution, this is a 0.1 molar solution. I'm going to get rid of my arrow for now. And I can't move whatever that solute is from one place to the other, then that's a problem because what this membrane really wants is to have the same concentration on both sides. If it's not the same, then we have issues, okay? Because what's going to happen is that since the solute can't move, the water will, and the water will move from where I have low concentration to where I have high concentration to try and equalize those concentrations. So I get my H2O moving from this side to this side. As it moves to the side that has the higher concentration, the pressure on this side goes up and the pressure on this side goes down. That's the osmotic pressure. It's the difference that we're seeing there. Okay. So that pressure difference from this process is called the osmotic pressure. That's equal to pi, we call it pi, is equal to mRT. So M is the molarity, R is the gas constant, and T is the absolute temperature. So I can calculate what that pressure is. I will tell you right now, I will never ask you to do this. I hate doing these calculations, so I don't ask people to do it. It's just something in my head. I don't like to do it. But that's how this works. Now, might I ask you to explain to me what's going to happen if I have a situation like this that I've drawn right here? Yes, I might. I might say to you that I have this concentration on this side of the membrane, this concentration on the other side of the membrane. It's a semi-permeable membrane. What's going to happen? Is the water going to move? Where is it going to move? Where's the pressure going to be higher? That kind of thing. So that is something that I do expect, is that from a quantitative perspective, or from a qualitative perspective, you can answer those questions. Okay? All right. Now, the other things that we see is that there are temperature changes. Okay? So we see freezing point depression and boiling point elevation. Now, here in the South, we don't talk much about freezing point depression because we don't really see it here. But if you live somewhere where it snows, they often go out and they'll put down sand or they'll put down salt. And the reason that they do that is because it lowers the temperature at which that water freezes. That's a freezing point depression. And that's a practical application of the ability to change that temperature. Okay. Now, using different materials is, there are reasons why we use different materials. We'll talk about that in a few minutes. But that is something that is considered when we talk about this. Now, freezing point depression and boiling point elevation are tied to each other. So the boiling point elevation is, as I add things to this solution, I'm less able to boil, right? So my vapor pressure is lower because I can't get out of solution. And so my boiling point has to be raised because I have to get the same pressure of this material above the solution as the atmospheric pressure to be able to boil. That's the definition of boiling. So I need to be able to get more of that material out, even though the vapor pressure is lower, so that temperature goes up because I need more energy. Okay. This has a practical application as well. And the practical application that we see with this is that people add salt to their water when they're cooking pasta. Now, people will give you lots of reasons that they do this. They'll say that they do it for flavor, which, okay, that's true. All right, that is very true. Other people will tell you that they do it because it makes it cook faster. And that's true, but not really. The reason that happens, because it does cook faster, is because that temperature is higher. So if it's a higher temperature, it cooks faster. So yes, that's the effect. It is a higher temperature at which it cooks, but that is because that temperature has been raised. Okay. The equations that we use for these are very, very simple. So you'll see that the change in temperature for freezing, delta TF, is equal to KF times M. KF is the mole freezing point depression constant in degrees C per mole. That's awesome. It's not something that you can know or that you would have to be able to memorize. That is not something I would expect you to memorize. There are some of them that are given in the exam handouts. I think. Or did I take them out here? Oh, I think I took them out here. Yep, I took them out. So that is something that would have to be given to you, either KF or KB. Our formula for the boiling point elevation is exactly the same. Delta TB, the change in the boiling point temperature, is equal to that mole boiling point elevation constant in degrees C per mole times the molality. Okay, so it's the same format. That's awesome because that means I have less to remember. It doesn't matter which direction I'm going in my temperature, I just have that one equation. Now, is that equation in your useful equations? Actually, I believe that is. Yes, it is. But what you'll see is it's a little bit different, and we'll talk about why it's a little bit different in just a few minutes. Now, you'll also see in these equations that the osmotic pressure one is there, and that's because it sometimes occurs on the final. So you may see it on the final, therefore you will have the equation for it. Okay. So we can do these things. Also, I can calculate how much that temperature is going to change based on the molality of my solution and this KF or KB. Awesome. So let's look at what that would do. Consider the dissolution of glucose in water. The water is 150 grams. There are 12.6 grams of glucose. What is the change in temperature for the freezing point and the boiling point of this solution? Okay, a couple of things that I need to know to be able to do this. The KF, that freezing point depression, is 1.86 degrees C per mole. Awesome. KB is 0.52 degrees C per mole, smaller. So I would expect the temperature to go up less in the boiling point part than it does go down in the freezing point part. Okay. Now I know that my equation is delta TF is equal to KF times the molality. That molality, again, molality being equal to the moles of my solute over the kilograms of that solution. Okay. So I can calculate the number of moles by taking that 12.6 grams. I divide it by the molecular weight of glucose, which is 180.156. Okay, that gives me 0.0699 moles per kilogram. I divide that by the 0.5 kilograms, and that gives me 0.466 mole. Okay, awesome. So my delta TF equals 1.86 degrees C per molal times 0.466 molal, and that's 0.867 degrees C. So the freezing point at that molality concentration is going to be my initial freezing point minus that change to give me negative 0.867 degrees C. Now, is that a huge change? No, it's not. It really isn't. And that's one of those things that we have to be able to look at. So if I'm going to put salt or something down to try and change that temperature, is it really going to be effective? So that's one of the reasons why some places do it, some places don't. You know, not everywhere that it snows, it's done. In California, that is never done. Okay. But in New York, it's a very common practice. Right? Okay. When we talk about our boiling point elevation, we're looking at the same kind of equation. Delta TB is equal to KB times the molality. So we're talking about the same solution as before. So we need to calculate the change in temperature based on KB. So I've already calculated that molality. So I see delta TB equals KB times the molality. My KB is at 0.52 degrees C per molal. I multiply that by the 0.466 molal, and that gives me 0.242 degrees C, meaning that my new boiling point is 100 degrees C plus the 0.242 degrees C, or 100.242. All right, so it goes up, not as much as we went down, but it does go up. Awesome. All right, so that's our calculations for that. We need to calculate the molality of solution. We need to know what that constant is, whether it's a boiling point elevation or a freezing point depression. We calculate the change in temperature, and then if we're asked for the actual temperature at which that occurs, that phase change, then we have to correct the one that we've been given. So if it's a freezing point depression, we'd subtract it. If it's a boiling point elevation, we'd add. So questions about that? Sorry. All right. Now we can use this to find the molar mass of things, all right? I know that if I rearrange this equation, I have that the molality, is equal to the delta TF over the KF, right? So from the molality, I can calculate the number of moles if I know the mass of the solution, okay? From there, if we recover and measure the mass of the solid, I can find the molar mass, okay? So if I have a 7.85 gram sample of a compound with an empirical formula of C5H4, and that's dissolved in 301 grams of benzene, the KF of benzene is 5.12 degrees C per molal. The freezing point of the solution is 1.05 degrees C below that of pure benzene. What are the molar mass and the molecular formula? Okay, so I know that molality is equal to the change in that temperature over the KF. So my change in the temperature was the 1.05 degrees C. My KF is at 5.12. So that tells me that the molality is 0.205. Okay, awesome. I know that I have 301 grams of benzene, so I convert that to kilograms. And then I can multiply that by the 0.205 moles per kilogram, and that gives me 0.0617 moles that I have present. Now I can take that mass, that 7.85 grams, divided by the number of moles that I just calculated, and that gives me 127 grams per mole. If I look at this empirical formula, and I can calculate a mass for that empirical formula, it's approximately 64. So if I take the mass that I just calculated, that molecular mass of 127 grams per mole, and I divide that by the 64 grams per mole that's for the C5H4, that's 2. So I know that my molecular formula is 2 times what that empirical formula is, so it's C10H8. Okay. Will I ask you to do some practice with this? Yes. Is this a huge part of what I'm going to ask you to calculate? No, I don't think it is. I tend not to ask these kinds of questions. I tend to ask what's the boiling point elevation. So very similar to this one. So I'll give you a scenario where you have some amount of solute that's been added to a particular solution, what's the boiling point elevation and the freezing point depression. I may also ask you, what's the boiling point elevation and what's the new freezing point? So that in one of those, I'm looking for delta T. In the other one, I'm looking for the TF, okay, as opposed to the delta T. All right. So questions about that? Okay. Now I said that eventually we would have to consider what kind of effect we would get from things that dissolve when they go into solution. So remember, some things dissolve when they go into solution. Any ionic compound, when it goes into solution, such as sodium chloride, becomes an Na plus a Cl minus. Okay, those are ions that are electrostatically charged to each other. When they get into an aqueous solution, they separate. That means that I then have two particles, not just one. Okay, but it's not always two. When we talk about Mg3PO4, that dissociates, and my I for that is going to be, I get 3 magnesiums because there's a 3 right here, and I get 2 phosphates because there's a 2 right there. So that's 5 particles that I get from that magnesium phosphate. Okay, so that's a much bigger deal when I have that. Now we call that thing an I. It's called a Van't Hoff factor. And that tells me how many particles do I get when this thing goes into solution. So things that don't dissolve, like glucose, is an I of 1, because every particle that I put in becomes 1 particle in that solution. So it's a 1. NaCl is going to have an I of 2, because I get 2 particles for every NaCl that I put in. Mg3PO4 is going to be an I of 5, because I get those 5 particles for every one of those that I put in. That is going to have to be part of those calculations that we have done. All right. So that affects the following equations. Delta TF is then equal to that I times KF times M. Delta TB equals I times KB times M. And my osmotic pressure is equal to I times the molarity times gas constant times the temperature. So I don't like to have to remember this for multiple scenarios. So I only memorize these. And okay, that's what you're going to see on the test, is exactly this. Because if it doesn't come apart and then I is 1, then it disappears. So that's why I do it that way. I think it's a little strange to talk about. When I was a student, we didn't talk about it separately. And I think it's a little strange, but I also think it's a little clearer. That's why I'm trying to do it that way, okay? So that changes things. So if we look at our freezing point depression and our boiling point elevation, they look exactly the same way they did, except I have that I in there, okay? So I now have that I in front of the KFM, I have that I in front of the KBM, all right? And I can do a freezing point depression. If I consider the dissolution of magnesium phosphate in water, water is 150 grams, there are 12.6 grams of magnesium phosphate, which has a molecular weight of 262.855 grams per mole. What's the change in temperature for the freezing point and boiling point of this solution? Okay, so we're talking about a very similar scenario to what we talked about previously. We have the same mass of our solution that we're talking about. We have the same mass of material that we're putting in. It's a different molecular weight. It's also a different number of particles. So those are the two things that are different. Since we're talking about water, our Kf is still 1.86 degrees C per mole, and our Kb is still 0.52 degrees C per mole. Our delta Tf equals I Kf M. M is equal to 12.6 grams divided by that 262.855 grams per mole, which gives me 0.049 moles. Okay, divided by my, oh, that unit is in the wrong place, sorry, divided by my 0.15 grams, or kilograms, and that gives me 0.319 moles. So that should not be there. So this is my number of moles here. That should actually say mole there. That 150 doesn't belong there. Okay, and that's 0.319 mole out. So my delta TF is equal to that I, which again for magnesium phosphate is 5, times 1.86 degrees C per mole times that 0.319 mole gives me 2.97 degrees C. And that means that my freezing point is now going to be at negative 2.97 degrees C. That's a much bigger difference. Now, is it huge? But no, it's not, but it's much bigger. And so this is why we have to have a consideration when we're considering, okay, as a town, if I'm going to put something down, am I going to put down something that doesn't dissolve or something that does? Okay. And that's one of the things that we have to think about, because magnesium phosphate is a really expensive thing, so we don't usually use it. Sodium chloride table salt is very cheap, so we can use that. But then it's corrosive to half of the universe, so is that really a good thing for us to do? You know, it's never just as simple as, oh, this has the best effect, let's use that. Because it's not just that effect that we have to consider, okay? So there's that. We can look at our boiling point elevation for the same scenario. So delta TB is equal to I kBm. We still have our I of 5. Our Kb is 0.52 degrees C per mole. And our molality is 0.319 mole. And that gives me 0.831 degrees C. Okay. So my new boiling point is 100.831 degrees C. Awesome. So we can, and the process has not changed. We calculate the molality. We have to know how many particles we get from that material. So we need to know what the formula is. Okay. And then we can, calculate this based on the information that we have from the tables. Okay. Whatever values that we've been given, we can do that. So there are questions about that. And one of the other things that people talk about, and this is a thing in some textbooks and some reference places where you see this equation is going to have a minus sign. The reason that it has a minus sign is to remind you that if you do this correction, you're going to have to subtract it. So if the minus sign is there, then we just add that value to my original. Okay, this is not included because this textbook expects that you remember that if it's a freezing point depression, it's going to be lower. And if it's a boiling point elevation, it's going to be higher. Okay, so that is part of why it's not present. Okay, questions about that? So things that you might get asked about in terms of what we have talked about today. Define things like supersaturated. Supersaturated contains more solute than it should at that temperature. What's a gas-solid solution? Well, that's a gas that contains some solid in it. Okay, some of the old style halogen lights had that kind of stuff that happened. And what's osmotic pressure? The pressure that builds because of the movement of water through a semi-permeable membrane. Okay. Freezing point depression, right, is the change in temperature because of the solute in the solution. Okay, freezing point goes down. What's a colligative property? It's a property that depends only on the number of particles, not on what those particles are. A Van Hoff factor, I, is how many particles I get from each thing that I dissolve. So again, for something like magnesium phosphate, I is going to be 5. What's a surface tension? That's the additional force that exists at the surface because everything is pulling down and to the sides. Okay, so we have a higher tension at the surface because of the directionality of that pull. Calculate the freezing point depression and boiling point elevation of 31.65 grams of magnesium phosphate and 55.6 grams of acetic acid, which has a Kb of 3.07 degrees C per mole and a Tb of 118 degrees C. The density is 1.05 grams per milliliter. Kf is 3.9 degrees C per mole. Tf is 16.6 degrees C. And the molecular weight is 60.05 grams per mole for acetic acid. Okay. So if I'm looking for a freezing point depression and a boiling point elevation, the general form that I'm going to be looking at is that delta T is equal to the I K M. Now, if it's a freezing point, it's going to be that one If it's a boiling point, it's going to be this one. Okay. That means I need molality. So I will need a molality. And I need that for the 31.65 grams of Mg2PO4. No, sorry. Mg3PO4 2. And again, that's because my Mg, being a group 2 metal, was a 2+. My phosphate, PO4, is a 3-. That is its charge in the polyatomic ions table. So the charge on this becomes a subscript here. The charge on this becomes a subscript here because they're not the same. So that's how I know that this is the formula that I need for magnesium phosphate, which has an I of 5. Okay. I need to know the molecular weight of magnesium phosphate, which I was not given. This molecular weight is for acetic acid. Okay. And the reason that I know that is because it's too small for magnesium phosphate. And when we talked about magnesium phosphate previously, we said that the molecular weight was 262.855. So there are reasons that you might be given the molecular weight for materials that are your solvent, okay? And I know why that one is there, but there is no molecular weight given for the solute, so we need to know what that is. So again, that was 285 or 262.855. Okay. Now, I know that there are 55.6 milliliters of acetic acid. I know that the density is 1.05 grams per milliliter. I know that my Kb equals 3.07 degrees C per mol. My Tb equals 118 degrees C. I know that my Kf is 3.9 degrees C per mol. And my Tf is 16.6 degrees C. Yeah, okay. Just making sure I had all the information pulled out of that. Now, two calculations that I want to do, delta T, F, and F. Delta T, F, and delta TB. I need to calculate a molality for both of them. So I'm going to calculate that molality first. My molality, again, moles per kilogram. So I have 31.65 grams of Mg3PO4 I divide that by the molecular weight, which is the 262.855 grams per mole of Mg2PO4. It gets rid of my grams and leaves me with moles of that material. If I want molality, I need that over kilograms. And I know that I was given an amount of 55.6 milliliters. So I have an option. I can either do the 55.6 milliliters and multiply that by the 1.05 grams per milliliter to get the mass over here separate from that. I can do that. Right? In which case I would just put that result in here. But I don't like to separate my calculations because I know that I need to deal with these things without having rounded them. So for me, I know that it needs to be kilograms on the bottom. So I'm going to put that 1.05 grams per milliliter here. I know that to get the number of grams, I need to have this 55.65 milliliters to cancel the milliliters there. And I know that there are 1,000 grams per kilogram. So for me, that's how I would set that up. But I can do this calculation here, the 55.6 times 1.05. That tells me that this is 58.38 grams, which if I divide that by 1,000 is 0.05838 kilograms. Okay. So 31.65 divides 262.85. And if I do that happy calculation, that gives me a molality of 2.06. And at this point, I would write the whole thing down because I'm going to continue to use that. And that's my molal that I have calculated for that particular solution. Now, I'm not rounding this at this point because I'm not reporting that number. I'm going to continue to use it. So I haven't bothered to round it. I shouldn't round it until I'm done with all my calculations. Okay, fine. So I now want to calculate my delta TF and delta TB. So because I wrote this in this order, KB, TB over here, and KF, TF over here, I'm going to calculate delta TB first because that makes my head happy. That's equal to my I times the KB times the molality. My I again is 5. My KB is the 3.07 degrees C per mol. And then I have the 2.060683365 mol. And that number (31.63), and I'm looking, I have 4 sig figs in this mass. KBs are considered infinitely known. TBs are considered infinitely known. So I'm looking at the 4 sig figs that are present here. Okay. So my conversion factors are all considered to be infinitely known. So I need my 4 sig figs from this. So I would report this as 31.63. And that's degree C because the molality is canceled there. Okay. So that's my change. Delta TB has gone up by 31.63 degrees C. All right. And I wanted the freezing point depression and the boiling point elevation, which means that I'm not looking for the new boiling temperature. I just want that change. Okay. So I've calculated my change. That one's done. If I want to look at delta TF, that's IKFM. I have my I is 5. My KF is 3.9 degrees C per mol. And then my molality is 2.060683365. And that's molal. That will cancel there. That will give me 5 times 3.9 times 2.060683365. And again, 4 sig figs that I'm going to report, 40.18 degrees C. Okay, so those are the calculations that I was asked to do for that. Now, did I get some information that I didn't need? Yes, I absolutely did. But it's fairly common when I write a question like this for me to include all of those pieces of information because I have to look them up in the same place, just in case I decide to ask what's the final temperature for something. So you may get information that you don't necessarily need. All right, one of the other things that you can see from this is that I was planning on doing some unit conversions to get to something that required the molecular weight of that solvent, like a mole fraction, but I decided not to do it. So that molecular weight, which is for the acetic acid, does not apply either. Okay. Now, the fact that it was listed as a molecular weight, if you got this question on a test and you didn't know that that was the wrong one, if you used it, that's fine. Okay. If you use it appropriately, that's all that matters. I need to see that you've used it appropriately. But of course, that means that I need to be able to see your work. All right. So your work needs to come into me so that I can see that. If you give me some number that doesn't make sense compared to what I've done, I don't know why you got the number that you got. So I don't know if you were on the right track or not. So I can't give partial credit for that unless I can see the work that you did. Using that wrong molecular weight when I wrote the question badly should automatically go away. But again, I can't make an assumption that you did the calculation right or didn't do the calculation right. So I only have two options. I can either throw the question out, or I can keep the question and grade partial credit with what I have available. Okay. And so that's some of what you'll see. I did throw one of the questions out on exam 2 because I didn't give a volume for something. So I did throw that question out. All right. And that's okay. So the curve will reflect that. Now, are there any questions, comments, problems about what we talked about today? Okay, it's up to you now. You need to go and do your practice with all of these things so that you're comfortable doing these calculations. Remember that there are questions on D2L that are written the way that I will write these questions, i.e. the practice for this section. And then there are stepped down practice if you don't really understand the calculations to help you walk through them in the in-class practice. So depending on what kind of practice you need, they're both available. All right. If you have any questions, comments, problems, please let me know. Like I said, I will be releasing those grades fairly shortly. We will talk about the test on Monday, as well as doing a lecture, and then we will have a bunch of time for review next week for exam 3 and the final. That's everything I've got for you guys today, unless you want to hang out and ask questions.
Hey, I missed like the biggest fraction of the lecture because of that. I just want to know, like, I'll of course watch like the lecture that you upload, and I'll like able to watch it and stuff. But what was the main equation you used for it? Like, you know how the last lecture we used like M1 T1 is equal to something like that. What was an
Well,
equation for it?
well, no, there are a couple of equations that came up in this one, 3 of which are listed in the useful equations table. So one is the algebraic pressure, and I can, that's this one right here.
Okay.
One is the boiling point elevation. This is the freezing point depression. So those are the main equations that were given.
Okay. And then that's how you just solve the problem, the last one, using these 3 equations?
I used 2 of those equations for that.
Okay. I mean, it depends on the question, right? So,
Correct. I don't typically ask about these. I don't like to calculate the pressures, but I do talk about it in the qualitative sense. So rather than asking you to calculate the values, I'll ask you something. Let me get to it. So my semi-permeable membrane is here. I have a low concentration on this side, a high concentration on this side. That membrane cannot pass that solute. It can only pass water. And so it's going to move water from this side to this side to equalize those concentrations. That means that this pressure goes up, this pressure goes down. So that's the kind of question that you would get is, here's this, I have this solution on this side, I have this solution on this side. What can move, i.e. the water, not the solute? Where will the pressure go up? Where will the pressure go down? Kind of deal.
Okay. Makes more sense. Okay, thanks. I think
You're
that'd be
welcome.
all. I'll just watch the lecture.
Okay.
Hi.
How are you?
Good. I for one, the Alex, like I said, I've made some major progress on those, but they're so picky with like the sig figs that you use, and they also when they give you like examples of how to work the problems out, they don't use like the conversion table that you have us set up. They use like really weird formulas to get the answers.
Yeah, they break everything down into single step kind of
Yeah, it's a
deal.
really small.
Right. That is correct.
Um, so I've been like going to like explain the problem and then just using the way they do it,
Yeah,
get the
that's
answer.
fine.
And then it made me like forget how to do it our way because I kept doing it that way.
Well, but it's really not any different. Okay. And it really doesn't matter to me how you do it. What matters to me is that you get to where you need to go. So if they're setting it up such that they're going from grams to moles is one step, and then from moles to moles is a second step, and then from moles to grams is a third step, which is usually what they do. All of those are things that I do in that big calculation. They just do it in 3 separate steps.
Mhm. Okay. And then I was doing the reactions lab
Mm-hmm.
and I couldn't get past this part right here.
Okay, show me.
And I know, okay. Okay. So it's sodium hydroxide and nickel, what's NO3?
Nitrate.
Nitrate. So if I was to get the yield for this, it would be sodium nitrate. So it'd be
Yes.
3NO.
Yes. Well, it'd be NaNO3, correct.
But then when I picked NaO3 aqueous, it said no, that's not right.
Well, okay, so you need 2 products. That's one thing. So you need to determine what the other product is, and you need to make sure that they're both in the right phase. So when I look at this, I know that one of my products is going to be the NaNO3. That's correct. The other one is going to be that NiOH2. So I
Right.
know Ni is a 2 plus, so I need 2 OHs, that NiOH2. And of course, if I look, I can see that, where's that rule? Oh, except for those in rule 1, carbonates, hydroxides, oxides, and phosphates are insoluble. That's rule 5. So I know that that hydroxide is insoluble, so it's going to be a solid.
Right.
So you need to select the NiOH2 solid and the NaNO3 aqueous.
Yeah, I tried to pick them, but it won't let, like when I pick one.
You need to hold down, I think it's the control key, and I'll let you pick a second one.
Oh.
It's either the control key or the alt key. And you need to hold it down while you do it.
Okay. So I'm clicking and holding down control.
But
Oh, do I have to drag it like this?
I mean, that worked.
Oh, maybe that's what it is. Okay. It doesn't explain to you how to do that. It just says select all that apply.
I think if you click that question mark
Mhm.
right next to select all that apply,
Oh,
it tells you right there.
okay. Okay. Okay.
I didn't think it told me either. I just started poking stuff and then I went, oh yeah, it does say that.
Okay. All right then. I should have it now. I just was not sure how to get to, like, I knew what I was creating. I couldn't select 2 of them, but
Right.
should
Yep.
I
No,
should.
I understand. Yeah.
Okay, thank you so much.
You are welcome. And I sent an email about Sunday.
Yes, I responded 3 p.m. is fine.
Okay.
So next week we have Monday's lecture, which is lecture 14, and then the rest of the week we're gonna be doing
Reviews.
for the 3rd exam or for
Exam 3 and the final, because exam 3, while it's focused mostly on the 3rd set of material, involves everything anyway. So it's a good time to review for the final as well.
Okay, perfect. So we have lecture Monday, lecture 14. Exam 3 is the 24th. We'll be reviewing on the 19th and the 21st for the final.
Correct.
And
Correct.
Okay.
And then we'll have another review day the day after the exam. So we have some time to talk about the exam itself.
Okay. And that's the 26th. And our lab final is
21st to the 23rd, this weekend.
next weekend.
Oh, yeah, next weekend. Sorry.
Okay. Sounds good. All right. Thank you so much.
You're
Oh,
welcome.
one more
Yeah.
thing.
Yes.
How many points will the exam 3 be in D2L?
It will end up being 100. Even though I have taken 6 points off, I didn't remove it from the total. I just awarded it to everybody.
Okay, so right now the total points we have in D2L is 38.8. So how many
And
will show in D2L?
for
Like
exam
the
2,
like for your grade as a whole. So right now I'm looking at my grade and it says 28.4.
out of 38.8, and that's because not everything is due yet. So that total is based on the percentages that are due. So not everything is due yet. At the end of the term, it'll be 100.
Okay. Right. Um and with I'm just trying to see like what it's gonna be like once you put the exam grade in, I'm trying to see like where my percentage will be.
Well, the exam itself is out of 100 points. In the scheme of the grades, each exam is 33.3% of 35% of your grade. So 1/3 of the 35% that are the hourly exams. 2 of those count, 1 does not.
Okay. So it'll be like 11 points or something like that. 11 and a half. If you do 35 times divided by 3, it'd be 11 and a half. But 1 is dropped. Or am I not doing that calculation?
Well, I don't, I'm not entirely sure. I'd have to sit down and actually do the math. And
It's okay. It's okay. I just want to know how many points it would be.
I mean, and of course, in theory, it would be 11 points for each one, but because one gets dropped, they end up being more than that.
Mm-hmm. Okay. All right. Sounds good. Thank you so much.
You're welcome. And I will talk to you soon.
Yes, ma'am.
Thanks.